JJ 君のために60分プレゼンをお願いしております。今日は残念ながら通訳がおりませんので、山本祐介さんが省訳ということで、サクッと訳しながらということですね。はい。そちらをご覧いただきながら、プレゼンをお聞きいただければと思います。では、let's start.
All right, thank you. Okay, good evening, everyone. Thank you for coming. I am going to talk tonight about a little bit about JRuby and Ruby, about how Invokedynamic, the new feature in Java 7, works, and how the two work together, how we're making JRuby and Ruby run fast on the JVM. So there's my basic information. I have been at Red Hat for about 3 years now, a bit over 3 years, working on JRuby full-time for almost 10 years. First at Sun Microsystems, then at a company called Engineard, is graciously sponsoring our work on JRuby. So here is the agenda for my talk. A brief intro to JRuby and Ruby. How many are familiar with Ruby, the language? Okay, that's good. A very short introduction, and then talk about how JRuby works. An overview of the basic, the new JVM feature. Some examples of Invokedynamic in a very general, high-level sense. And then also we'll talk about JRuby and how we use Invokedynamic, how it's making Ruby run fast for us. So first, JRuby. Of course, on the JVM, or Ruby and Java together. You can call Java libraries from Ruby. In the case of in bulk, you can plug Ruby code into Java applications. It's running together on the same VM, Ruby and Java together. And the project is actually fairly old. It was first created in 2001. A German gentleman named Jan Arne Petersen, who I've never met, originally created this. He wanted to try to parse Ruby on the JVM. And once he had a parser, he said, well, why don't we continue on and make a Ruby implementation as well? And it moved along well for a while. But in about 2005, this framework called Rails came along and changed everything. And that was about when I got involved in JRuby. I was a Java architect at the time, applications for several years. And I found Ruby and thought it was a beautiful language. I really wanted to use it. But being a Java guy, obviously I thought maybe there's a way that can combine these. And I found the JRuby project. I saw that it needed some help. And so I started working on improving JRuby. And so then fast forward to this year, we just released JRuby 9000, which is our latest major release. We've caught up on compatibility. We're compatible with the current version of CRuby. And we're starting to do all the great optimizations we've always wanted now, using Invokedynamic, using our new compiler. So that's 10 years of working on a Ruby implementation full-time. And obviously there must be something about Ruby I like to work on it for that long. So we'll take a quick look at Ruby, created right here in Japan, in Matsue, by Yukihiro Matsumoto, 1995, about the same age as Java. It's celebrated its 20th. It's a dynamically typed language, so calls are dynamically dispatched at runtime. Object-oriented, very much in the way that Smalltalk is. And everything is an object. So numbers are objects, true and false are objects. Everything's floating around in memory as an object. You can call methods on numbers, and so on. And then probably one of the more interesting sides of Ruby is very tight integration with C and Unix. It's kind of been traditionally used as a Unix scripting language, a glue language for all of the pieces of Unix that you use. We're now using that as a glue language for JVM applications, Java applications. And this is mainly what I'll be talking about tonight, how we make this dynamic type, dynamic dispatch, all that work well on the JVM, and perform like we want it to. A short snippet of Ruby code. We create a class called hello. We open a class up. Here we have the constructor is called initialize. We are assigning an instance variable called name to this variable passed in to the constructor. Here we have another method, display. We are printing out hello, whatever the name is. And here you see to insert values into a string. If you don't know Ruby, and I found that fascinating. And so I've spent 10 years working on JRuby. So, method calls. Let's start there. Ruby equals lots and lots and lots of method calls. Thousands of method calls. Because everything's an object, almost everything you do in Ruby is a method call. These are a few Ruby commands. So just starting JRuby up, basic startup of JRuby, 1,000 method calls happen. Installing Rails gems, and this is Rails plus all of its dependencies, 315,000 method calls. Generating a new application, 606,000 method calls. And just displaying a simple result from a database, 16,000 method calls. So obviously, we need fast for Ruby applications to run well. So in JRuby, here we have another simple Ruby example. Foo calls bar, bar calls baz, and so on. And looks roughly like this, conceptually like this. Before Invokedynamic, this between logic, all of the logic for calling, by hand. Go look at the object, find the method, make the call. And because we had all that logic in the way, the JVM doesn't optimize as well as we'd like. It can't see through this big block of logic here. So if we look at this more graphically, we do our foo call. The foo call goes up into JRuby, looks at the object's class and finds the foo method, calls it, and then caches it here, saves it for next time. And then each time we make this call, we need to still the same method. We need to guard it, test it. And that logic confuses the JVM, all doing that over and over again. Not as fast as we want. This is a very small piece of JRuby's code for doing this. We have our call come in, we get the class, the Ruby class of the object. We grab the current cache, if that cache is okay. Otherwise, we have to look it up again. Search for the method, check that it's actually there, cache it, and then proceed. This all gets in the way of the JVM. We need a way to sweep this away so the JVM can optimize better. So JRuby before Invokedynamic, all of these issues. Now let's proceed and talk about what Invokedynamic is and what it does for us. This is a quote from the first edition of the JVM specification. In the future, we will consider bounded extensions to the Java virtual machine to provide better support for other languages. So even in the very first version of the JVM, the authors were thinking about new languages, not just Java. Now for 10 years, nothing really changed in the JVM specification to support other languages. Languages would come, they would have to do the same work JRuby did, didn't optimize as well as they'd like, didn't perform like we wanted. And then in about 2005 or so, we started working with Sun Microsystems on Invokedynamic. So the goals of Invokedynamic. added a new bytecode that allows us to optimize dynamic languages. We added a library of function pointers, fast pointers, and some adapter code for them. Faster than reflection. Everyone's used reflection at some point. This is meant to be direct calls, a direct pointer to a function. There's some logic for caching those values so that we don't have to look them up again and again. And the bottom line, we wanted Invokedynamic to be flexible, very adaptable, so that future languages, future Java features, we wouldn't need to do this all over again. Support features for the future as well. So how does Invokedynamic work? So if we look at the way the JVM is structured, there are, in a standard JVM, there is 4 different types of calls. Static calls, like current time milliseconds. Virtual calls, which is a method call on a concrete object, not an interface. Interface calls, like calling against list or collection. And then what they call special calls, constructor, super calls, private calls, everything else. And these boil down to a set of 4 JVM bytecodes. So here we have our static, invoke virtual, invoke interface, and invoke special, with the encoded signature for each method here. And now if we look at how these work internally, you'll see that they're all very similar. Invoke virtual checks that it's the same type of object, checks that we've got the same type of arguments, looks up the method, caches it. Mostly the same here, and here, and here. Largely the same logic for all of these types of calls. So Invokedynamic basically allows us to plug in those steps. Instead of having a fixed sequence that it does, it calls our language and asks, how do I find this method? How do I call it? Then it plugs that back in, and it uses our logic rather than invoke virtual, rather than invoke special, and so on. Let's look a little bit more graphically. So here we have our JVM, represented by a telephone switchboard, because that's what the JVM really does. It just routes calls around, right? So up at the top, we've got our Invokedynamic. The Invokedynamic is going to be in the JVM, we'll call back to our language. Our language is represented by our switchboard operator here. Calls our language logic. Our language goes and gets those function pointers, finds the method to call. Then it gives that method back to the JVM. And then this is where the magic happens. Now, the JVM sees that this Invokedynamic calls this method, and all the rest of that can go away. So that logic that kept JRuby from optimizing just disappears. And now it optimizes like it's a normal Java call. And if we look at this in terms of in the Invokedynamic specification, we're talking about call sites here, where the call happens. We're talking about Bootstrap logic that sets the call site up. And method handles are our function pointers. So let's start by talking about what method handles are. So I mentioned that method handles are like function pointers. That's use, is to get pointers to methods somewhere in the system. It can also manipulate arguments, do some flow control, and it can be optimized by the JVM, much faster than reflection. So we'll walk through how this works. The interesting package here is java.lang.invoke, added in Java 7. And the 3 interesting classes here are method handles, which is a factory for getting function pointers. Method type, which just represents what the parameters and return value are for a given method. and MethodHandle, which is that callable, that function pointer object. So we first need to get a MethodHandles.lookup, and this is what we use to get those function pointers, to get a pointer to a method, a pointer to a field. These are various things that we can get access to, methods and constructors, obviously, individual fields, either static fields or instance fields, and array elements. We can also set and get array elements using method handles. Here are some of the basic functions. So you want to find a static method or a virtual method. Call find static, find virtual. Pointers to the fields, getters, setters, static getters, etc. Here's a quick example. We get our method handle lookup object. Here we're going to basically do the same. This is the example code, system.getProperty foo. We ask the lookup, find static on the system class. Get property is the name of the method. We know it returns a string, and it takes one string as an argument. Now we have a method handle that we can call. m2.invoke foo, same result as what we did up here. Very simple example. A little more complicated example here. System.getProperty get java.home. So here's our method type again: string.class, returns string and takes a string argument. Find static, get property, invoke with java.home. Okay, simple enough. How about an instance method? So here we're calling printLine on system.out, which is a print stream. We do method type. printLine does not return anything, so it's a void return, and it takes one object. Find virtual on the print stream class. printLine is the name of the method. There's our type for the method type. And then we pass system out in and our string hello world. So there's an instance method as a method handle. Okay, so that's how we can get basic function pointers. It's fairly easy to do. But we may want to manipulate arguments as they enter. We may want to add an argument or remove an argument. So there's a number of adapters on the method handles class for doing argument manipulation, changing the arguments, for doing some flow control, if, then, else. And it's sort of like writing your own little command pattern objects, your own little function objects. So we'll talk about arguments first and just show a couple examples. So here we have our get property handle that we created before. So this is system.getProperty. And let's say we always want it to be getProperty java.home. We take our handle, we insert an argument, java.home, so we don't have to pass it anymore. Now we get a Java home function object that we can call without passing any arguments in. All as one little function object. The same example with system out printLine. It's kind of annoying to pass system out in every time, so we can insert argument at 0, system dot. We have a system out printLine function object that can do that call every time. Okay, and you can see how we can adapt that, add more arguments, remove arguments. More advanced here, what about flow control? Let's say we want to do if then else logic in our handle. Guard with test is a method on method handles, and it essentially implements a Boolean branch. You give it 3 targets. One is the condition, a function method handle that will return a Boolean value, a true path that will be followed for true, the then path, and a false path for else. So this is our example Java code. We're just going to get a random Boolean value. And if it's true, we're going to uppercase the input string. If it's false, we're going to lowercase the input string. So here we have our random Boolean handle. This is going to be our test. Randomly will return true or false when it's called. Here we have made previously a 2 uppercase handle, a 2 lowercase handle. And so here we have our guard with test, our if, then, and else. And now we have a function object all in one that will randomly uppercase or lowercase the string. Another layer of adaptation we can do around these function pointers. Okay, so there's a lot more to handle. The first time the JVM sees it, we'll call our Bootstrap, which is just a normal Java method. We say, here's the Invokedynamic, here's the Bootstrap logic for it. Our Bootstrap will return a call site object. Then every time after that, all it's going to do is call that call site object, which is just a function object itself. We'll call it every time. So this allows us to plug into the JVM and make it do our own logic. A call site just is a method handle holder. You insert a method handle into it. Some of them you can replace the method handle later on, but the JVM sees this as replacing the Invokedynamic. Now this actually represents that call. So here's a very simple Bootstrap method called simple Bootstrap. So we have a lookup on a method name that we want to call and a method type, just like when we look up a function pointer. Here, we're going to find static. We're going to look on the simple binding class, some class that we have in our system, for that name and that type. We create a new constant call site that change after this, and we return it. And now this will only be called once by the JVM. So we've now gone and programmatically told it, looked up what method to call. The JVM will install that and run that method from now on. Simplest possible case of a Bootstrap here. Now I mentioned sometimes the target of a call site can be changed. Mutable call sites, in addition to constant call sites. So for our example, we want to alternate between 2 methods. We'll call first and print out first, then we switch and call second, and so that each time we call this, it goes back and forth, for a simple example. Here's our Bootstrap. This time we're going to use a mutable call site. We want to call first the first time through. So we get a handle using the code you saw earlier, similar code. We're going to pass that call site in so that we can change it later on, set the target for the call site, and return it. Now if we look at the first method, we see that we've got our call site passed in. We're going to get a handle to the second method, change the call the other method now, and then do our logic. Then we'll call the second method. Next time through, calls this, we get a handle to the first method, change the target again, and it will go back and forth this way. Dynamically changing what method is going to be called. And the JVM will optimize this, just like any other piece of Java code. Okay, so now putting all of this together here. The bytecode in the JVM gets the call site. We look up a method handle that points at some target method. The call site holds on to it, and then the guard, that if then else, makes sure we're always calling the same one. Just tests it to make sure we've got the right one. And this is all the pieces that we need for dynamic languages, for doing a dynamic call. We can look up the method at runtime, change it if necessary, and let the JVM optimize it. So let's talk about how Invokedynamic is being used within JRuby itself. So obviously, we use it for doing method calls, dynamic invocation. We always look at the target object to find the methods, and these objects can potentially change their method table, so we have to even check if they're being modified. And then in our language, we have a specific way to check the type. Looking at our original Ruby example here, these are the calls. So puts is a dynamic call. The .new here to create an object is a dynamic call. And our display call here is also dynamic, just so you know which pieces we're talking about here. So there's our code before Invokedynamic, and we want to get rid of that. We want to tell the JVM how to do this for us. So we'll follow it through again. Foo call goes to the JVM, and it looks up the foo method. Then the foo method actually goes all the way back to the original code, replaces the Invokedynamic. Now the JVM doesn't have to be involved. It'll call that every time. We don't have to do all of this logic every single time we do a Ruby call. So to the JVM, it looks like a direct call now. We've taken all of that extra logic out of there, and then we can get all of the great JVM optimizations. So we can have Ruby code inline into Ruby, Java code inline into Java, or Java code inline into Ruby, all optimizes like it's a piece of Java code. So does this work performance-wise? Well, this is a comparison of JRuby with CRuby. I'm missing the labels here. But this is just 10 million calls to an empty method. So dynamically dispatch a method call. And that's well over 10 times faster. The interesting thing here is, let's see here, where did that slide go? Okay, so this is, I'm going to fix something right now. Let's do this and that. Hold on one moment, please. Okay. So here, that makes it a little more clear. This is 10 million calls to an empty method body. So we're just measuring the overhead of a call, basically. This is CRuby, the C implementation of Ruby. This is JRuby doing 10 million calls. And this control here is just the overhead of the benchmark itself. Okay? And if we look at that more closely, we can see that the overhead of the benchmark compared to the method calls, it's only about 0.03 seconds that it's actually adding on here for 10 million method calls. And this is what we'd expect. These are empty methods. If you did this in Java, it should optimize like this. It should optimize away. Invokedynamic makes it possible for Ruby to optimize that well, just the same way. Okay. So another place we use Invokedynamic in JRuby is for looking up for lazy values, like we have a string or a regular expression. We don't necessarily want to create all of the regular expressions right away, so we do it lazily. And then we use Invokedynamic to plug it in, so it's only created once. So for example, the string part here, we will create that string object just once, and then it will be plugged back into the code by the JVM. How does this look? We've got our lazy lookup over on the side. That goes to the JVM. We do our computation lazily, and the JVM pulls it all the way back. Now it actually looks like a constant value to the JVM. We don't have to go look it up in an array. We don't have to look it up in a hash. It's optimized as if it was just part of the original code. More interesting than just caching a string value is for looking at Ruby's constants. So Ruby's constants are not, they're mostly constant. They can be modified, but it's very rarely done, and it's discouraged. So for constants in Ruby, we want to look up the value and ideally save it for the future. It's probably never going to change. So let's just put a simple guard in there, a test, and then save that value forever. So here, the only constant lookup is getting the reference to the hello class. And so between creating this hello class, this lookup, somebody could have changed hello. But like I said, it's very rarely done. It's discouraged. So for a constant lookup, this is a comparison again of CRuby versus JRuby, looking up the same constant over and over again, which is a dynamic operation in Ruby. And again, JRuby's time compared to the control is basically just a small amount of overhead. The JVM can see that we have a constant value. Even though it might change, it still optimizes it as though it never will. And that's part of the magic of Invokedynamic. We also use this for looking up instance variables. So in Ruby, when you have an instance variable, a field, as in Java, it's dynamically added to the object. So objects grow as it's needed at runtime. That means we don't have a static way of getting to fields, like in Java. In Java, the field's always in the same place in the object, statically determined. In Ruby, we have to look up the offset, figure out where in the value will be stored, and then we can cache that. So ideally not look it up again. Just go straight into the object every time, get that value out, and then if we do see another type of object, then we'll modify it. We'll change that logic. But it basically allows the JVM to optimize Ruby instance variables as fast as a regular Java field, directly into the object. So here are the instance variable accesses. This is setting the name variable, and this is retrieving it. Walking through how this actually is done in JRuby. So we've got our puts at foo here, where we need to look up foo instance variable. We go to the object, we find the offset. That offset comes back, and from then on we just use that cached value. And we wire that with Invokedynamic so that it's directly accessing the field. MRI, the CRuby, actually does fairly well here. It actually can optimize to what we're doing. But again, Invokedynamic making a huge difference on performance here. Very little overhead for looking up a variable, as it should be as in Java. It actually optimizes pretty close to a standard Java field access. So you can kind of see that all of these pieces, almost all of this code here in Ruby, uses Invokedynamic in some way. We're using it very heavily. And these were all very simple benchmarks, synthetic benchmarks. Let's look at some things that are actually more useful. So real world numbers on this. We'll start a little less than real world. Some mathematical algorithms here. So bench fractal is just a Mandelbrot generator. It has a lot of integer loops. It has some floating point math, something that Java would do very well and Ruby maybe not as much. The flip-flop fractal generator is a Julia generator. And this code is very strange. I don't really understand how it works. So I'm not going to talk much about I think this was made as a joke using a strange Ruby feature. Okay, so here's our Mandelbrot generator, just dumps it to the console. And we're just going to iterate over this for a while and see what the performance is. So this is current Ruby, Ruby 2.2, versus JRuby with Invokedynamic. And this is the time in seconds. And again, JRuby is in the neighborhood of 5 to 7 times faster than CRuby for a real benchmark now, not just a silly method call benchmark. One thing you will notice here, it takes a minute for it to warm up, and that's the JVM doing that first Invokedynamic, then optimizing it like it's regular Java. So we speed up pretty quickly. This is the Julia set generator. And here we see again a similar ratio. JRuby handily beating CRuby on a fairly simple piece of mathematical code. And this is continuing to improve over time as JRuby improves, as Invokedynamic improves. All right, so a few more benchmarks here that are a little bit more real world now. We have a base 64 encoder. We have Richards, which is sort of a VM simulator written in this case in Ruby, and a very simple neural network implementation. So this is the numbers for JRuby without Invokedynamic. And it's pretty good. This is how much faster it is than CRuby. Here, 1.3 times faster, 1.5 times faster, and 1.9. So certainly faster even without Invokedynamic. But then Invokedynamic really changes it. So here, again, 2.6 times, 3.4. Invokedynamic really helping us optimize Ruby code. And this is really no change to the Ruby code at all, just using a better JVM feature to optimize this code. And now this is my favorite one, actually. So this final one, it's an implementation of a red-black tree in both Ruby and as a C extension, C code. So this is Ruby 2.2 running the pure Ruby version of this red-black tree, doing a bunch of inserts, some tree traversals, some deletes, and so on. For this benchmark, it takes about 2.5 seconds. And this is where CRuby users often will turn to C code to get performance. And it helps. It definitely does help. So about 5 times faster to implement the red-black tree in C, and then call that from Ruby code. And now where it really gets interesting, JRuby running a Ruby implementation with Invokedynamic, actually beating Ruby with the C code. It all optimizes together. Invokedynamic makes it optimize like Java code. And again, this is going to continue to improve as we do more and more optimizations in JRuby. That's pretty cool. So, future work here. We're obviously using Invokedynamic for many, many parts of Ruby. Lots of Ruby features that need Invokedynamic. But we think there's more we can do, some more creative uses of Invokedynamic. We also, in JRuby 9000, have a new optimizing compiler that will let us be smarter about the code that we give the JVM. Not expect the JVM to optimize as much, do a little work on our own. So these two combined, I think within the next year, we should be able to get JRuby running very close to Java speed for most things. And we're getting there bit by bit. We're also working directly with the folks at Oracle on the OpenJDK team to continue optimizing. They run JRuby as one of their primary benchmarks. They try our code out. They make optimizations to method handles, to Invokedynamic. And this goes back and forth. We continue to work with them over time. So every version of the JVM makes JRuby faster, and we make better use of it. And that's about all I have today. Please check out JRuby if you're at all interested in Ruby on the JVM. If anybody wants a JRuby sticker, I have those too, and you're welcome to take a few if you want. And I think we have plenty of time for questions. And I think we can have someone translate too, if necessary. So thank you very much. We'll have some questions.
ありがとうございました。じゃあ質問がある方、はい、どうぞ。いいですか。あ、はい。マイクちょっと待って。はい。
So I have actually two questions. So one is that, if my understanding is correct, a Ruby method needs to be a Java method, needs to be compiled into Java method so that a method handler can point it. That case, because Java system is Java type system is statically typed, that method needs to have some static types for the argument and return type. And method caching happens for each of those types, right? Then how is the method represented in Java?
Okay, so how is the method represented to deal with the static type signature and so on? Basically, we end up erasing all those types to our object interface. So every Ruby method compiles down to a list of iRuby object arguments. And for Ruby, the only thing that matters in looking up the method is the name. Unlike Java, where there's overloads, Ruby doesn't have any overloading. So all we need to know is that it's type of the object and what the name of the method is. We can cache that all the way back and then do the invocation directly with Invokedynamic.
I see. So I see. Okay, thank you very much. And the other question is that, so Invokedynamic is fast when it caches the looked app method, and it should not be fast when it's not cached because it needs to look up the function. When I run Invoke, because it's a command line tool, it runs a lot of methods just once. And I think in that case, Invokedynamic does not help. Is that correct?
Right. Yeah. So when you only do one call, we end up doing that lookup. We get no benefit out of caching it, right? And so that is one reason that JRuby by default doesn't use Invokedynamic for all of the calls. We use the simpler logic because Invokedynamic takes a little while to warm up. It has a little bit more. So Invokedynamic you would turn on in, say, a test and production environment. Or for benchmarking, you would turn it on. But to make the command line run faster, use the original logic, just to avoid Invokedynamic's slowness at the beginning.
So does it mean JRuby itself does have a sort of tracing to track number of method calls? And then if that exceeds certain threshold, it enables the Invokedynamic optimization.
Right, exactly. So we have a number of thresholds. First of all, JRuby, like the JVM, it starts out interpreting Ruby code. When that code runs enough times, then we turn it into JVM bytecode. When it turns into JVM bytecode, then we can use Invokedynamic. So we start up fairly quickly without JVM bytecode, but long-term performance will catch up with a compiled language.
Thank you very much.
Sure. Any other questions?
I think Invokedynamic does not help when we call Ruby methods from Java program. So in that case, method calls is not so fast, as I understand. Is that correct?
So there are many ways to call Ruby code from Java. If you're just dynamically dispatching, like rubyObject.call method, that will look up every time. There's nowhere to cache it. So that would be the slow lookup every time. If you have a Ruby object implement a Java interface, though, the interface methods implement this same caching. So, for example, if you do a runnable implementation in Ruby, every time run is called, we should be using a cached version of the method. We want to do that in more places, so that, but it's anywhere that you can actually have a normal Java call, we should cache it. It should optimize like I showed here. All right.
他にいらっしゃいますか?
This one in the middle.
I'm just curious that are you expecting that the invoke dynamic is used in lambda expression?
Yeah, so this a nice side effect of Invokedynamic is that it's helped make some Java features easier to implement. In Java 8, lambdas, basically Java's blocks, Java's closures, use Invokedynamic to lazily create the object, the function object, and then use it forever. So avoiding the anonymous inner class overhead. And we expected that things like this would happen, that Invokedynamic would be useful for more than just Ruby or dynamic languages. So Lambda's using it. The Java 10 generic reification, the generics work, will also use it. Pretty much every new Java feature could potentially use Invokedynamic to optimize better. So it's an amazing toolbox.
Thank you very much.
他に質問?
So I have two questions. So one is regarding the instance variable access. So if we do not use Invokedynamic, so instance variable access is implemented in hash table. So it is not good, but it's not bad. I mean, if we use Invokedynamic, so when we use Invokedynamic, so if cache is hit, but I imagine it's very slow if cache is not hit. So on the other hand, if we use hash table, even if the cache is not hit, it is not so bad. So how do you avoid such a bad situation when you use Invokedynamic?
So to summarize the question, if we don't use Invokedynamic, it would be like a hash table lookup every time. So it wouldn't be as fast as Invokedynamic, but it would be consistent. Consistently the same hash table. And yeah, this is true. The way that we improve the cache miss is that when we do the Invokedynamic, we will actually save a few different targets. So if it's 2 or 3 different types of objects, we'll have 2 or 3 different offsets, and we'll know which one to use. And then if it's not one of those, then we just fall back on the hash table. In the miss case, when the cache is missed, but not much more than just a hash table. So the worst case is largely hash table lookup.
Okay, thank you. So the other question is regarding the optimization for Invokedynamic in JVM. So currently, I think the method target caching is optimization for Invokedynamic in the JVM side. What optimization do you want to do in the future?
Well, so we've already done some things that the JVM can't do. So for example, the JVM will optimize up to 2 targets, 2 method call targets at a site. JRuby will optimize 6. We chain them together, and that was experimentally about how many we could cache before it became too much overhead. The things that we'd like to see more of, we'd like the JVM to see if there's temporary objects being used across that call and eliminate those. It can do that for Java to Java calls, but not for Invokedynamic calls right now. We mentioned that there's overhead with the initial Invokedynamic call. We'd like to possibly do a simple version of Invokedynamic until it looks hot, until there's a lot of calls. and then do the more complicated binding that the JVM will optimize. Other things that we might like to do. There are new Ruby features coming along that we're going to use Invokedynamic to optimize. The biggest one is refinements. Refinements is a Ruby feature that allows dynamically scoped method lookup. So within this particular area called, we can do that better with Invokedynamic than the C implementation. And that's still a work to be done. So little edge cases and new Ruby features that are using Invokedynamic.
Okay, thank you very much.
他に質問はありますか。多分日本語で答えてもゆうすけさんが訳してくれると思う。よろしいですか。じゃあこれでおしまいにしたいと思います。最後に古橋さんとチャールズさんに盛大な拍手をお願いします。Thank you very much.